Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll continue Chapter 10 about automated model selection for multiple regression and discuss several other model selection procedures and criteria. We're going to focus actually on the criteria here. We're going to talk about R-squared, adjusted R-squared, and the Mallows CP statistic. So we're familiar with R-squared as the proportion of variation explained by the model over the grand mean. And we always want to maximize this. And we know that when we add variables that are important, that R-squared will increase by a substantial amount. And there's some point where adding further variables makes R-squared increase, but in insignificant ways. Okay? It's a mathematical fact that R-squared can't decrease as you add variables. It can either stay the same, which is almost never the case when you've got actual data, and will typically always increase even if, trivial amounts. And so we can use R-squared to help us select variables, but then it becomes sort of a judgment call about when to stop, because does the added complexity of adding a variable increase R-squared enough to warrant that additional complexity? So that is what brings us to adjusted R-squared. We want to maximize the adjusted R-squared, and the adjustment to R-squared is a penalty for complexity. And it's defined in this way. I've got this notation of R bar, which is not great notation, I admit, but it's the notation I'm using for adjusted R-squared. And over on the right-hand side is the R-squared that we know, and then there's all this 1 minus business. So let's unpack this and understand what's happening. Let's start with an empty model. So P is a number of predictors in the regression model, in addition to the intercept. So the intercept doesn't count. So P is the number of X variables. So if P was 0 and we only had the grand mean, then we'd have n minus 1 divided by n minus 1. So this ratio would be equal to 1. So that goes away in the multiplication. And then we have 1 minus 1, which is 0, so that goes away. And then we have a minus, which is a positive, R-squared. So when P equals 0, the adjusted R-squared equals R-squared. That's a perfect starting place. Now, let's see what happens as you add predictors. So if P equals 1, okay, we'll just add one predictor. What happens? Well, we know that R-squared is not going to decrease. And just for sake of simplifying the discussion, I'll say that R-squared will increase. Okay, even though it is theoretically possible that it stays the same, it basically never does. It always increases some tiny amount. So we put in one predictor, and R-squared increases. So if R-squared is the proportion of variation in the response that the model explains, 1 minus R-squared is the variation that the model does not explain. Okay, that's the unexplained variability. That's the variation in the residuals. It's related to that. So this number will decrease, 1 minus R-squared, because we've explained more variability by adding a variable. So we get a decrease in the unexplained variability. What's happening with this fraction? So when P goes from 0 to 1, then we have n minus 2. So if n minus 1 divided by n minus 2, this fraction is now greater than 1. Okay, so this fraction will increase as P increases. Okay, so as we add variables, the unexplained variability will decrease, and this fraction will increase. And there's a balance here. Okay, if we add important variables, the amount of reduction of unexplained variability will decrease quickly, but this penalty will increase slowly. And at some point, the additional decrease, the tiny trivial amount of decrease that you get in the 1 minus r squared is so small that actually the penalty increases more than the decrease of unexplained variability. And so it's that balance. So as long as this decrease grows faster than the penalty, then adjusted r squared will go up. But at some point the penalty will grow faster than the decrease, and then the adjusted r squared will decrease again. And so that's the point which gives you the best model. It's the balance between the penalty and the unexplained variability. So some properties of adjusted r squared are that the adjustment is always, will never be larger than r squared. Okay, it's equal when p equals 0, and otherwise adjusted r squared will always be a bit smaller because of this penalty. If two models have the same number of variables, then the model with the larger r squared also has the same adjusted r squared, or larger adjusted r squared. That's because you've got the same penalty out front. Adjusted r squared penalizes the complex models, and it is possible that the adjusted r squared can be less than 0. If you've got a model that explains very little variability in y, you can add a bunch of unimportant variables. R squared won't really increase, which means this part won't really decrease, but the penalty will really take over. And you've got 1 minus this number times 1 and plus r squared. And if r squared is close to 0, this penalty can be substantially bigger than 1, and you can end up with a negative number. So, third criterion is Mallow's CP statistic, which measures the adequacy of predictions from a model relative to those obtained from the full model. So we're using the full model as the baseline. That's in linear model theory, the full model is the best model. It's the one that explains the data appropriately. And the only reason for simplifying it is to help us have a simpler explanation of what the relationships are. And in this case, we want to minimize CP. So we want to maximize the r squareds, and we want to minimize CP. And this is going to take a little bit of explaining as well. So the Mallow CP statistic is defined in this way. So let's talk through each of these terms. So let's start with p minus 1. P is the number of variables in a given model. Actually, let's start with this. Sigma squared hat full. So the sigma squared of the full model, that is our reference model. That is the estimate of the variance of the residuals in the full model. And as you remove x variables from your model to a reduced model, you'll have more and more unexplained variance. Okay? So this term won't change because this is based on the full model. But what will change for your given model is the residual sums of squares. Now, if we just think about the full model, the residual sums of squares for the full model is actually in the variance of the full model down in the denominator. In fact, this denominator is the residual sums of squares for the full model divided by the degrees of freedom, which is, say, p plus 1. So in this denominator, we have the residual sums of squares divided by the residual degrees of freedom in this denominator, which means that for the full model, this numerator is the residual sums of squares. This denominator is the residual sums of squares divided by the degrees of freedom. So that ratio is just the residual degrees of freedom. So if this whole term is the residual degrees of freedom minus the residual degrees of freedom, that equals 0. Plus p plus 1, that's the CP statistic for the full model. It equals p plus 1. Now what happens when we reduce the model so that p goes from the full number of predictors, which in my initial part of the chapter is k, is the total number of predictors, to a smaller number, p. So in that case, we have the full model, which stays, that quantity stays the same, but now the residual sums of squares is going to increase a little bit because we have fewer predictors in the model, we're explaining less variability. So this residual sums of squares goes up, but the residual degrees of freedom decreases by 1 unit. And so the question is this ratio is it increasing faster than the degrees of freedom is decreasing? Okay, and so the best models will be those that are minimize this quantity, and we should only consider models that are not bigger than p plus 1. All right, so models with CP roughly p plus 1 or less merit further consideration, and we'll take a look at comparing several of these criteria with the Peruvian-Indian data set. So the LEAPS package is one of several packages that help with model selection. So I'm going to start with the full model here. I'm going to fit that linear model and put it into this linear model object. And then the LEAPS package, so I've already loaded the library up here, we're going to use the LEAPS function to generate the R-squared statistic for several best models. And this is going to do best subset selection, which means that, so of these 7 variables, there's different sizes of model. So for example, models of size 1, where p equals 1, includes only 1 variable. So n best equals 5 means that we're going to choose the 5 best models with only 1 variable. So we've got 7 variables, so that means there's 5 of the 7 single parameter models are going to be plotted. And then how many sets of 2 models are there? I don't know, 7 choose 2, whatever that is, some large number. But we're going to choose only the 5 best of those. So for example, we're going to fit the model with weight and height, and then weight and chin, and weight and forearm, and so on. And then we'll do height and chin, and height and forearm, and so on. And all the pairs up to pulse and age. And once we've got all those models, we'll look at all the R-squared values, and we'll choose the 5 best ones. All right, so the way the syntax of this function works, we've got the full model already. If you wrap it in this function we haven't seen before, model.matrix, that's going to put the appropriate possible sets of covariates into this variable x. We have our response variable as y. We select the method we're going to use. We select the best, how many models we're going to consider of each size of model, whether we have 1 predictor, 2 predictors, 3, and so on. And then the names of the variables, rather than just giving column names 1, 2, 3, 4, is I'm just going to pull out the column names of that model matrix. So we've got columns that are easy to read. The structure of this data set, so I'm putting that into leaps.r2. The structure has this variable which, and that indicates which variables are going to be in each model. We've got labels for the columns. We've got the size of each regression model. So notice there's 5 best ones with size 1, 5 best ones with size 2, and so on. And then we have the R-squared values for each of those models. And I'm going to plot that model. So let me pause for a moment, and before we look at the, let's look at the plot with that. We'll go back. Okay. All right. So along the horizontal axis, we have the size of the model. So 1 predictor, 2 predictors, 3 predictors, all the way up to 8 predictors. And on the vertical axis, we have the R-squared value. You can see on the last one of 8 predictors, there's only a single model. That makes sense. There's only one model with all 8 predictors in it. So you can see a slight increase in these points as you approach 8. And you can see 1 point way down here. So there's 3 dots in this upper left-hand corner. There's there's 3 variables basically that have the same R-squared value. There's a 4th model that has quite a bit lower R-squared, and then there's a 5th model which has 1 predictor that has a very low R-squared value. And then there's 2 models that aren't plotted here that do even worse than that. Once you've got 1 variable in the model, the 5 best ones that have 2 variables all have basically the same R-squared value. Same thing with 3 and 4, and they don't always clump quite as tightly as this, but that's the case in this data set. And if I scroll up for a moment and choose what the best model is by asking which model has the maximum R-squared value, that is that model includes actually all of the variables. And that's what we would have expected for R-squared. As you include variables, your R-squared increases, and the model with the largest R-squared almost certainly is the model with all the variables in it. All right, so let's look at adjusted R-squared. Same thing, except in the leaps function, we're going to choose method adjust R-squared. And let me scroll down to the plot. So along the horizontal axis, we have the size of the model. And now there's actually, it's a bit hard to see. Maybe if I zoom in a bit, we can see it a little bit better. This actually goes up, and then there's sort of a peak somewhere, and then it decreases ever so slightly. So that penalty is bringing down the adjusted R-squared more than the R-squared is increasing. So if I scroll up now to and ask which model has the maximum adjusted R-squared and plot the names for that model, we see a model that has 4 variables: weight, height, chin fold, and the year age variable. So that is the model that's chosen with adjusted R-squared. Let's look at the CP statistics. And in this case, we're trying to minimize CP. So we do the same thing with the leaps function, but we specify method CP. Capitalization matters here, capital C, lowercase p. And here I'm going to plot the CP statistics, and I'm also going to plot a line, which is basically a one-to-one line, which gives us a frame of reference for which models should even be considered. Models that are less than this line are worthy of consideration, and things that are greater aren't good enough. So we see here on the largest model that it intersects the line. That's basically p plus 1, or in this case I've plotted this without the intercept, so this is actually equal to p, 8, 8, and 8. And then as you have smaller models, you actually do quite a bit better than that line until you get a model that's too small, and then your CP statistic is too large. So maybe there's one model of size 3 worth considering, and then models of size 4, 5, 6, and 7, which might also be worth considering here. And in this case, I might just sort of by eye sort of be really curious about what that model is right there. So if I look at what the best model is selected by the CP statistic, we actually get this model here with weight and year age as the predictors.